Okay, now this chapter you need to call out all the trigonometry equation. What I mean by trigonometry? Sine, cos, and theta. So you have a right angle triangular. You have a theta. Let's say this is A, this is B, this is C. Tangent theta equal to A divided by B, opposite and side. Sine theta equal to A divided by C, opposite by hypotenuse. Cos theta equal to B divided by C, side divided by hypotenuse. Okay, so these are the three fundamental equations before you go into chapter 3. Chapter 3, you're looking at one object, which is a cube object. Cube object and hexagonal object. Six shape. Look at these two shapes. Okay. We now in week 3. So we'll look at crystal structure. Okay, crystal structure also one of the popular question for test 1. Okay. So introduction, why we study crystal structure? Because we have all these minerals around us, minerals. So they have different kinds of name, different kind of colors. And there's an explanation why the crystal have this kind of shape, this kind of shape, this kind of shape in this chapter. So in this chapter, you should able, through calculation, you should able to predict the shape of the crystal that going to form based on calculation. Okay. We will not ask you about the color, but it will ask you the form of the crystal that's going to form. Okay. Okay. Now the word crystalline, it means there is an order or there's a pattern, repeated pattern on how they arrange themselves. So if you see the question asks you a crystalline solid, it means there's a pattern repeating, like you're building a Lego, like Lego bricks. You join them together and then you get the shape. Okay, so example of crystalline materials, they are metals, alloy, and ceramic materials. So this chapter will link you to metal, alloy, and ceramic material. You will link to all these names. Okay, then some materials, they are not arranged in the long range and repeated manner. So they are only have short range order, means very short range order. Material with only short range order, they are called amorphous, without any form, or non-crystalline. Okay, so this chapter mainly focus on crystalline materials. First, before we able to draw the shape, we use a network called lattice, space lattice. Right? So there's a certain way of atoms arranging themselves. So we need a direction or a map. For example, you define a map using X, Y, and Z direction. But in material science, you define the arrangement by lattice, space lattice. So space lattice, for example, the one you see on the screen here. So this is a crystalline structure. Again, why this one is a crystalline? The pattern is repeating again and again and again. For example, you see the four shape, there's 4 cube repeating and repeating, like stacking to each other, like a Lego bricks repeating themselves. So before we start this space lattice, we given them a few alphabet. We have a A. So you pick one of the atom at the one corner. Then x-axis means not x-axis, but the one that going out from the screen is A. Going to the x-axis is B. Going to Z direction is C. So you have A, B, and C. there's an angle between the two vector here, which is alpha, beta, and gamma. Alpha is B and C, beta and A and C, gamma is A and B. So this one is important. By changing the alpha, beta, gamma, and ABC numbers, it gives you a certain name of that cubic. Okay. So these are the fundamental on when deriving a certain crystalline structure. Okay. All right. So there are 7 types of unit cell, right? 7 types of unit cell. So unit cell, this is a unit cell. Unit cell is 1 unit of cell or space or lattice. So 1, 2, 3, 4, 5, 6, 7. Okay, so it might take some time to memorize these 7. First one, the fundamental one, cubic. Cubic is a cube. So the 4 side, the A equal to B equal to C. So it's a very same side of cube. And the angle, alpha, beta, gamma, they are 90 degrees. So you get a cube. So the name for the crystal structure is called cubic. Okay. Crystal structure, you have cubic. Then space lattice here, you will study simple cubic, body-centered cubic, face-centered cubic. So later, in the later slide, we will give a simple name. Body-centered cubic is BCC, face-centered cubic FCC. So you will have simple cubic. Normally, it won't simple cubic come out 1 time in the final. Simple cubic means the normal cubic that you see in mathematics, right? But it's still one question come out in one of the final exam question. It's a bonus question actually. Yeah? Okay, then the second one is called tetragonal, and the relationship ABC, gamma, alpha, beta, gamma is given in this table. Orthogonic same, and the rest also same. You'll see on this table. So this is your revision slides when it comes to your test 1 and also your final exam. Okay, very useful. This table will help you to define what is this, what is the crystal system you have. Okay, okay. So this one you see this one before, right? So there is a difference between crystal system and space lattice. So don't confuse between this one and this one. Cubic crystal system and space lattice system. Okay. Okay. Now, one scientist, he derived 14 standard unit cell that could describe all the lattice network. So there are 14 from 7 just now. One scientist derived this seven, and it derived to 14. 14. Okay. So we won't go through all 14. The most you will go through is 6 from here. Okay, 3 is the main important one. So we will go one by one. So we hope that by end of this lecture, we can finish chapter 3. We hope, because this is also another big chapter. Okay, so we start with 4 names: simple cubic, body-centered, face-centered, and base-centered. Simple, body-centered, face-centered, and base-centered. Okay. So in cubic system, there are 3 types of unit cell. So there are 4 types of, there are differences. There are 4 types of basic type of unit cell. So there are 1, 2, 3, 4. But inside cubic system, there are 3 type unit cell. So simple, body-centered, and fast. We're going to learn these 3. We're going to learn these 3. Okay. In orthogonic, there are another 4. Orthogonic, there are all 4 types of presented. So it's inside here. inside here. So we go one by one. Okay. First, simple cubic, we'll use simple SC to represent simple cubic. Second one is called BCC, body-centered cubic, and FCC, face-centered cubic. Okay. Now you need to imagine a little bit. I don't have the tools. I don't have the balls for the sphere for the illustration. So you look at, there are two type of presentation also. The photo that you see of all the diagram you see here, actually they are same. Above and below, they are representing the same thing, but there are certain name for that one. But we go for the arrangement of the atom first. The first one is called simple cubic. Simple cubic means you have 8 atoms on the cubic. Means each corner you have 1 atoms. That is simple cubic. Whereas very high chances I won't ask you this simple cubic question. Unless you score very weak in your test one, then I will try to help you in final exam with simple cubic. Okay, means simple cubic means it will have 8 atoms in 1 unit cell. Okay. Second, body-centered. Body-centered means inside the body there's something. For this case, you have 1 red color at the center of the cell. So number of atoms inside BCC will be 9 atoms or 9 sphere. 9 sphere. Okay. So body means some inside the body, inside the sphere, or not in the sphere, inside the unit cell. You have 9. 8, 4 at the top, 4 at the below, and 1 at the center. Another one, FCC, face. Face means in 1 cube, how many face you have? 1 cube, 6 face. 6 faces, so each face will have 1 red dot at the center of the face. Okay, can you imagine? Imagine. So this is a 3D dimensional. So if its body means only 1 complete sphere at the center, if it's face, then you have sphere at the side of the each of the face of the cube. Okay, we'll go one by one slowly to explain to you how to draw or how to calculate for each type of the cubic. Okay, now first we go through the simple cubic, BCC and FCC. Go slowly. Okay. Okay, simple cubic example for simple cubic is salt NaCl, sodium chloride. Okay. Okay. Now, most of the tutorial question, not most, but normally we'll start with NaCl to explain about this diagram. Okay, but we will go a bit faster. We go straight into body-centered, face-centered, and then we'll go to hexagonal close spec. Right. So just now you have seen 3 types. In this one, you add 1 more. It's called hexagonal close spec, HCC. So basically, throughout this module, you'll see 4 type of crystal structure. Okay. Most of the tutorial question you see simple cubic, but in the exam you will see either one of these come up. Okay. Okay. So the first one, you see there's an atom inside the body. It's called BCC, body-centered, with 4 at the top, 4 at the bottom. And then this one is 1 atom, 1 sphere at each face. So this one is FCC. This one is hexagonal because on the top you are having hexagonal shape, and then you extend, it's like a prism, right? Okay, we go slowly. So the rest, this is just illustration on that. Okay, so the more complex it is, means the more denser, means more atoms that they can fit inside the cell, the unit cell. Okay. So the rest you read, the rest you read. Okay. Now we start with the PCC. As you can see on the diagram here, there's one atom at the center. So how you know is at the center, you just draw the line and then you join the intersection, you know that is a center. Okay. So we look at this sample. At room temperature is equal to the site. The site of this one is equal to, this one is ion, BCC ion. We look at ion. Ion is Fe. Ion is Fe, ferrum or ion. So at room temperature, the site of this one, A, B, C, they are 0.28 nanometer. Okay. So for ferrum, if unit cell of pure ion is lined up side by side, so in 1 meter cube, there will be so many unit cells. Okay, it means that this is one side of this one is 0.2287 nanometer. So in 1 mm, from here you measure 1 mm. So if you assembly lamp that are Lego bricks, total Lego bricks that you need to assembly 1 mm, you need 3.48 10 power 6 unit cell to assembly 1 mm. Okay, so you just take 1 mm, you convert m milli to 10 power 3 divided by 0.28. Nano is 10 negative 9. So negative 3, negative 9. So actually it becomes 6. Right? So 1 over 0.28, you get 3.48. Make sense? So the distance between atoms in crystal structure can be experimentally using X-ray diffraction analysis or XRD. XRD. So when you hear material scientists they mention, oh, I'm doing XRD analysis, means they are using the measurement of the distance here, then they know what is that element. They measure, they use X-ray to measure 1 cubic of distance, this one, here to here. They measure the A, B, and C. Then they go back to the database, or then they identify, oh, this is the element. Okay. So this is the XRD because we don't have that in INTI. I want to show you this one so that when you go out work later, you saw this one, you're not like, you're not shocked lah. At least you know, oh, this is XRD. Okay, so let's see what is XRD. Very expensive, this machine, a few million. So there is a reflector and receiver here. Okay, enunciator, this one shoot, and then this one receive. So by the angle of the refraction, they can calculate the length of the unit cell. So there's a peak received by the two angle there. So if you talk to any material scientist, the first graph they will show you is XRD graph. Okay. So these are the angle measured. There's a received signal. It's a peak, means there's a detection of certain reflection at that certain angle. So these are the one that shoot X-ray, and then there's a receiver there. So they will rotate the object, and then they will start scanning the thing. Okay, so this is XRD. Okay. Now this is the normal table that you will see in your final exam. Okay. Now you have the name of the metals. You have the constant, lattice constant, which is the A. What is A? If you draw a lattice, this is your A. Okay. Atomic radius in nanometer. What I mean by atomic radius? You still remember just now we tried to fit some sphere inside. So if the element is chromium, the radius of the chromium here is 0.125 nanometer in radius. Okay, so at this point, even sometime in the appendix in the question, you will see some helpful calculation formula there. Okay, we will prove this equation later. And the rest of aluminum, chromium, everything is there. But what is important for this slide is that there is a table for you to refer for your calculation later. Okay, that is more important. Okay. So this one is for BCC structure. Of course, in the exam, this one will be removed because we won't show you what is the crystal structure. You need to prove that. For example, chromium is BCC. So I will remove this one. You need to prove this value or prove this value. Okay, same with this one. I will remove this FCC things. Then maybe I pick one of these, go. You need to prove this value and this value using cube and trigonometry calculation. Okay, same with this one. I will remove this one. This is HCP, hexagonal close pack. Close pack. So you have chromium, you have A, C, radius, and so on. Later we will look at this. The most difficult question when you see this one, normally this one is one question itself, asks you about HCP. When you see this diagram, it means the whole question will be asking you this one, 25 marks will ask you about this one. Okay, normally this one will be question 4 or question 5. Okay, okay. So again, if you don't see this one come out in test, one question will also come out in final exam. So you either one. So and this is another table. So sometimes we will give you this table when you arrive at a certain calculation. So for example, aluminium is FCC, the radius is A, and so on. So just now, the few table you see, they are separated, they are organized at a certain BCC, FCC, or HCP. Okay. So sometimes when you see this one, means the question asks you some element inside here. Okay. So there's a certain calculation for BCC, FCC, and HCP. Okay. So we start with the BCC. There are three presentations of crystal structure. The first one is atomic site unit cell. So if the question asks you to represent your answer in atomic site unit cell, we expect you to draw the cube with a small sphere, small dot at each corner. Okay, like this. Use the hidden line. You have learned the CAD or technical drawing already. Yeah? So means the hidden face, you use the dotted line. So the first presentation is called atomic site unit cell. So of course, those solid line you can draw at the back, you also can draw, but I'll prefer to use hidden line. But if you can't stop yourself from using hidden line, it's okay, you use solid line. What is important is the sphere at the each corner, and the center is a small sphere and not big sphere. It's a small sphere. Second presentation is called hard sphere unit cell. Hard sphere unit cell means you imagine you're using a bowling ball kind of size of things, and then you laser cut them into cube, and you only see what is the laser cut outcome. Okay, so since we are talking about BCC, body-centered cubic, means there's one atom inside. So when you cut out BCC in the hard sphere, you will see one complete bowling ball at the center, and then quarter, 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 quarter. Means this is a quarter ball, quarter ball, quarter ball, quarter ball, and quarter ball. Makes sense. Okay. So another type is called insulated unit cell. Insulated, it means the one that you take from here. Insulated. Take this one out. Okay. So hard sphere means you draw the full bowling ball with the frame inside. Okay. Why you need the frame? Because you need to refer to the center sphere there. Right? Is BCC is body centered, means there's something inside the body. So inside body there's a complete sphere. Okay. Now before we move on, how to find the volume of the sphere? What is the equation? Over 3 pi r square. Square or cube? Square or cube? Sure. You say square, huh? You go and check, huh? Okay. So the statement come out. Each of these unit cell equivalent to 2 atoms per unit cell. Are you able to prove that each of, body-centered crystal structure, for one unit cell, each of these unit cell, they have 2 complete atoms inside there? Are you able to calculate? You use this one. Center already one complete one. Then the top got 4 corners. Each corner is quarter, 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 quarter. You join 4 quarter, you get half, right? But below one, you got 4 corners. Each corner is quarter, quarter, quarter. You join the 4 quarter, you get another half. So below half, but top half, join, you get 1 atoms. So total, you have 2 complete atoms for BCC. Makes sense? Can I? Who cannot get it? Can I? Okay. Huh? Huh? Cube, right? Okay. So for BCC, you have 2 atoms. This is the fundamental before we go deep, because later we will use this concept to build models. Build models. Any questions so far for BCC? So there are 3 presentations. In your calculation or in your scratching or in your answer, normally you'll use atomic site unit cell to solve question. Okay, and the question you will see normally in this way, this one, or we won't show you anything, we just give you the name of the unit cell. Okay, this will be part of your answer. Means we expect you to present your answer or solving answer in unit cell atomic site unit cell presentation. You don't need to draw this one. You don't need to draw this one. Okay, and most of the textbook out there, they will use hard sphere unit cell to show you the arrangement of atoms. Okay, so we already explained how to get 2 atoms. Right? Calculation is there. Right. So 1 atom at the center, 8 multiplied by 1/8 at each corner. So you get 2 atoms. Okay. So this is another presentation, same diagram, same. So this one, A is a reduced sphere. So just now, one textbook is called isolated cell. So sometimes they also name as reduced sphere unit cell. This is called reduced sphere. B is a hard sphere unit cell. Hard sphere unit cell, and C is a aggregated. Aggregated means stacking of the cell. Okay. So again, this one, A and C, normally you'll see in the question, in the assessment. B is your answer that we expect in your answer sheet. So we try to derive the relationship between the cube side with the A and the atomic radius. Okay. So this is important. It lay the foundation for the calculation for the other chapter. So okay, so okay, let me show you this one, and I'm not sure whether you're able to see all these things. I try to make it very quick. Nothing complex. It's just mathematics. Nothing complex here. So you know each side is A, right? You know each side is A. So this is we call right angle. So when you draw a diagonal thing, so you are seeing what? A, right angle. How to find this x? How do you find the length of x? Okay, x squared equal to a squared plus a squared, right? Correct. This one you learned in mathematics. So x equal to square root of 2a. So I already explained this one on whiteboard. Square root 2a. Why? Sorry. So you pull this one out, square root a, you get a. So I already explained square root 2a already. Okay. Once you have this one, you have a, right? You should able to find this one, right? Same concept. So you know that this one is square root 2a, and this one is a, and you're going to find this y, same, another right angle triangular, square root 2a, you're going to find the y. So y equal to square root a squared plus. Okay, or if you're lazy, you just change this one. You don't reduce this one, you straight away square root 2a squared. So here, get your y equal to a squared plus 2a squared, correct? Correct. So a squared plus 2a, what you get? So you get square root 3a squared. That's right. So that's why you get square root 3a. Make sense? Okay. Now, we are done with the trigonometry. Now we combine with the sphere concept. So BCC, if you draw your sphere inside, what do you see? BCC, you have one at the center. We have four at the corner. So this one you get another one. This you get another one. Of course, here you get another one. And here you get another one. Right? Get here like that. If you slide like that, if you slide the sphere like that, you slide this one. No lah, okay, not this one. I can also lah, but try to align with the slide. I slide. Okay. Same also lah, can lah. Okay, but slide like this. So you'll see one sphere here, one sphere here, one sphere here. Okay. So you know that one sphere, the radius is r, right? So this is r. This is also r. Diameter, one diameter equal to 2r. So this is 2r. So total 4r. So you combine the sphere dimension and the trigonometry equation that you link. Where is this 4r equal to? Equal to this one. Equal to your y, square root 3a. So the question asks you to relate a and r. You write 4r equal square root 3a. So we don't like this kind of format. We can either put in r in terms of a or a in terms of r, right? So to be easy, we write a at the left. So move your square root of 3 to the left. You get 4 divided by square root 3a. R. This is the first equation for the second half of this class. Very, very important for BCC. As you do more exercise, this one will come into your mind. You don't need to even think. But sometimes, most of the time, we'll ask you to prove this value. Means the explanation that I explained just now, you prove, then you substitute value. Let's say, how you prove this one is BCC, I go back to the table just now. How you apply this one? Prove that this one is BCC. If the value of R is 0.142, this one. Maybe I give you another one, the table just now. Okay. So proof that this is BCC if the R of the chromium is 0.125. Prove that chromium is having BCC crystal structure. You substitute chromium, R is 0.125. Substitute inside here, press your calculator, you get A equal to 0.299. Refer to appendix. Your answer is, you write like this. Refer to appendix A with A equals 0.299, R equal to 0.125. This is crystal structure BCC, and the element is chromium. Or you get something near to this number, something near. Okay. Okay. This is how you prove your value lah, and application of this value. Okay. This one you don't need to memorize one. If you see this one, you just derive at what you see on the screen here. It just take you like 30 minutes, or not 30 seconds. You draw a cube, draw the green color sphere, and then you derive from the base here, AA, find the hypotenuse, square root of 2, then A here, then find the hypotenuse for the diagonal. You find that is your y equal to square root of 3a, and then combine with the sphere radius. You are seeing 4r here, so 4r equal to this one. Rearrange the thing, you arrive at this equation. So I will encourage you not to memorize, but understand the concept, how you arrive at this one. It's more important. Okay? Because there are so many things that you need to memorize already. It's better you try to understand it, and then you derive from the foundation. It takes you like less than 30 seconds to get the value of this equation. Okay? Of course, if you can memorize, then memorize. If you have good memory, then go ahead. Okay, so this is the first equation. Oh, 5 o'clock already. Okay, we go a little bit more. Then we have a short break. Okay, so I did prove to you how to get A equal to 4r divided by square root of 3. Okay. Okay, so I also give you the some hints there. What is Pythagorean theorem, A, B, and C? If you forget, then you go ahead and have this one on your revision. Right. Next, we go to atomic packing factor. Means how you pack the thing by using equation. Right. Now, how many sphere you can fit inside the BCC just now? 2 atom, right? But you cannot say like 2 atom. How you prove it, right? You prove it using volume. Okay, using volume to prove the APF. Okay. Now, the thing is that how you prove atomic packing factor means how many atoms you can fit inside there, and then the concept is using volume. There are only two items here to focus on. One is the cube. What is the volume of the cube with the A side? How you find the volume? A cube, right? A cube, A times 3. How you calculate the volume of 2 sphere? This one multiplied by 2. 4 over 3 pi r cube multiplied by 2. Okay. So APF, you take the volume of the atom in unit cell, which means you have 2 atoms, means 4 over 3 pi r cube multiplied by 2 divided by volume of the unit cell, which is A. But you cannot take A. Why? Because A, you cannot solve this one. This one, the top part of the equation is in terms of R. This one is in terms of A. You cannot solve. But there's a relationship in BCC that you can use. Just now we derive A equal to 4 over 3, 4 divided by square root 3R. Take this one, substitute inside here. Substitute inside the below one, this one. You cube it. Then you cancel here and there, you arrive at 1 numbers. What is that number? Can you do the mathematics? Do it now. Prove that APF for BCC equal to 1 number. Can you do the calculation now? It's a simple cancellation by using. Sometimes you don't need to even press calculator. You just write the equation out. What is the volume of the atom in unit cell? Here, this one. You have 2 sphere, right? 2, 4 square root 3 pi r cube divided by volume is this one. 4 over cube. So what do you arrive? How you cancel? This is 8.3 pi r cube, 4 cube, square root 3 cube, r cube. So cancel here and there lah. You get one number. What is the number? 4 power 3 is what? 64, right? So here is 64. What? Equal to what? Equal to what? 3 square root of 3. Square root of 3 power 3 is what? If not, then use your calculator. Okay. So uh, 64. Or you can press your calculator lah, faster lah, I think. So you cancel your r cube. It's only one number there. So 8/3 pi square root 364. So you have square root 3, square root 3, 3/2 divided by 8 pi multiplied by 3. So 3 multiplied by 3 means what? 3 plus 1, you have 3, 5/2. Press your calculator lah. You got one number there, huh? Okay. So where's the number? Where's the packing factor for BCC? Okay. So you'll get 0.68, right? Is it 0.68? You calculate lah, huh? Calculate. You'll get 0.68. Okay. So this is the calculation for the one that I show on the whiteboard. Okay. We go maybe 20 more minutes, then we call it day. Straight. Okay. So this is how you calculate it. The top one, volume of the atom is 8 point something r cube. Volume of the cell is A3. You substitute the constant value, A equal to 4r square root 3. You substitute, you get 12.32 r square. You take this one divided by this one. The answer is 0.68. Okay. So this one also will be part of your final question 1, part A. Normally, they ask you to prove BCC APF equal to 0.68 by using the procedure like what I show on the screen here. Okay, means you will see a very short question, but the step is a lot. First diagram. Diagram normally will be 3 marks, and then the equation. You need to write APF equal to what divided by what. Then each step will give you marks. Yeah, so this one 3, this one 1 mark. Once you calculate this one 3 mark, and so on. It's quite a bonus mark there. Okay, any question for BCC? Now we go to FCC. You can convert to 100%. This is a ratio. You can put in a fraction form, or you can put in the ratio. You can put in percentage. Okay, so if you use this 0.68, you can leave as 0.68, or you can write in at the 68%. Okay. Okay. So means the atoms inside the cube there is 68%. So there are still 32% that you can fit inside there. Okay. So this kind of question is important when you do alloying. You need to make the metal stronger. You need to find the gap that you can fit in small molecule there. Normally it's nickel, Ni. You fit inside the small gap. There's still 32% gap for you to fit in. So once you fit in the space there, you make the product is stronger because it's able to move at a certain orientation. Yeah, the percentage actually is the gap that you can fill in. We will solve that empty space problem when it comes to alloy or strengthening mechanism. Okay, that is another chapter. So apply the same understanding for FCC. I'll go very fast on this one. If you understand BCC, I'll go very fast in FCC. FCC is just a change of name, and phase centered FCC because it's phase. So each phase have one atom. So when you pack, there's no atom at the middle. So when you pack, each phase will take half atoms. So how many atoms can you fit? Can you imagine? Four, me? Four, me? Try to imagine. Each phase have five half sphere. So this one form one, two side form one, then another side form another one, another top. So you have six phase, right? So each phase has half, so you have three sphere already. Then the corner, so it form one, so it's four. Four lah. Three is the phase, so six phases, each phases is half. Right? So you combine six phases, you get three sphere. And then the corner is half at the top, half at the bottom, then you get four. So you got quarter, so four lah. Same. You do the same calculation, but the A will not be the same. A will not be the same, but the same procedure. I will show you very fast. Okay, all agreed for sphere. So take home is that FCC is 4 atom, or not atom but 4 sphere . Okay, I'll show you very fast on the APC. Then we go home already. So same 3 presentation: atomic site unit, hard sphere, and isolated unit sphere. So APF, if you do calculation, it will be 0.74. What is different is the A is different. A is different. Okay, I'm going to go slow on this one because this is also very popular for tests. Okay, when you draw this sphere for FCC, so FCC, when you slide the cube into half, you slide this region. So you'll be seeing what? If you slide this region, you'll be seeing quarter here, then what else? Center. How the center look? Okay, never mind. Okay, this one you don't need to slide. This one you straight away look at the space. Look at the face. Okay, so you have same R, 2R, R, but this one is different. It's different. Okay, so already show you how 4 atoms already. So it's calculated by this one. So this one, is, you know the calculation for to get square root 2a, right? A, you get hypotenuse, you get square root of 2a, right? So yeah, a is a side, this one, a is a side. So you get a, then you get the hypotenuse. So you get square root of 2a. Then you know the radius, you compare to the sphere. So from one corner to one corner, is total is 4r, correct? Equal these two value, you get a new equation for FCC. FCC a bit simple. 4r equal to square root of 2a. Move the a, you get 4r square root of 2. Okay? So don't confuse FCC and BCC. BCC have one set of equation of a, FCC have one set of a. So that's why I encourage you to derive the equation from the unit cell rather than memorize. So sometimes you might confuse. Okay, but if you have very good memories, go ahead and memorize. Okay, okay, do the same. Prove that APF equal to 0.74. Same, take the volume of the sphere. You know that you have 4 atoms here. 4 multiplied by the volume, 4 over 3 pi r cubed, divided by a cubed. You know that for BCC, your a equal to 4 divided by square root of 2r. Rearrange the equation, cancel the r, cancel the pi, you will get 0.74. Make sense? Okay. So the example of FCC, BCC, FCC will be copper, lead, nickel, and iron. Okay. Memorize at least 3 examples from the table. In my slide, just now I saw you what is a BCC, FCC sample and HCP sample. Memorize 3 member in the table, because the question normally will ask you give 3 example of BCC, FCC, and HCP. Each one give 3. So memorize 3. Any 3 from the table just now. Make sense? Okay. So okay, go a little bit more on HCP, then we go home. All right. Now HCP is a very special structure. And last semester I don't ask question, but your semester I will ask question on this one. Because I cannot overlap the question every semester. So last semester I don't ask, so I ask this semester. Okay. If you understand, it will be easy, like the numbers I show on the whiteboard just now. But try to see how we calculate. So for HCP, you have 6, 1, 2, 3, 4, 5, 6 at the corner, 6 at the corner, and 1 at the center. Repeat the same for the bottom one. Then the center we have 3 more at the center. Okay, so you have how many? 6, 7, 14. 14 plus 3, 17. 17. Okay, so it's very complex. So you have the dimension of A and C. So just now for BCC, FCC, you already have A. HCP, you have one more, with the C, the height, the z-axis. Okay, so another one is this one, A, and then there's numbers here. So means you have okay, there's an angle here. You can break this hexagonal into 3 parabologram, the parallelogram. Parallelogram, you need is this shape. You can break the top into 3 sections. Same one. Okay. So, but since they are isometric, or means they are same They are same, so we only analyze one of the paralogic or parallelogram. Parallelogram. Okay. 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 So metal do not have this kind of hexagonal because the APF is too low for metal. But it can be for alloy. Okay, it can be for alloy. So both HCP and FCC structure, each atom surrounded by 12 atoms. Okay. So how do you take this statement? FCC, each atom is surrounded by 12 other atoms. We don't go deep into FCC first. We look at FCC. FCC is each phase have one atom. So you imagine you are this phase atom here. So you're actually touching 12 atom at the side. You try to imagine this is half, so this is another ball come out here. So you're going to touch 12 sphere. Try to imagine, go home and use the tennis ball to imagine. So there are 12. I mean, you try to imagine in 3D, like how this one atom is surrounding. So this one, you imagine you are tagging. Yes. Okay. So the rest you read, the rest you read. So APF for SCP is 0.74 also. Okay. So the atom marked as 1, this location is 1/6 of the atoms. Is this one is 1/6 of the atoms. But the atom located at number 2, see number 2 here, number 2, they are one of the 12 of the atom, means they touch 12 atom at the side. Okay, but this one you need to imagine a little bit because I don't have the tools. So yeah, so this one, number 1, you 1/6, 2 is 1/12. Okay, so the atom at the 8 corners of the cell collectively contribute to 1 atoms. Try to digest this statement. Atom at the 8 corners of the unit cell mean this one. 1, 2, 3, 4, 1, 2, 3, 4. We only look at like one unit inside the hemisphere, the hexagon. Okay, so those that mark as 1, you have 1, 2, 3, 4. You have 4 atoms that mark as 1. So 4 multiplied by 1/6. And then you have another 4 will contribute 1/12. You take this number, 2/3 plus 1/3, you get 1. Okay. Atom coordinate 3, this one is at the center inside the unit cell, but extends slightly beyond the bounded unit cell. So number 3 there is like centered within this one. Okay. So total number inside the HCP cell is 2. Yeah. So for HCP, it's 2 atoms. Okay. So I would highly recommend you go home and try to write this number. Try to draw this number and then the angle and 1, 2, 1, 2, 1 and 2 number, and then there's number 3 at the center. Okay. Number 1 is 1/6 atom. Side number 2 is 1/12. This one is 1 atom itself. So 1 plus 1, you get 2. Okay. So So in a case, 156 atom per unit cell. Why? In one complete HCP, you have 3 sets of this one, right? So one set is 2 atoms. So you have 3 sets. Means you multiply by 3, you have 6. So multiply by 6. Multiply by 3, you get 6 atoms. Okay. So the ratio of the height C here, this one, is in the ratio based on the side A. This one, how to find the C? There's a table just now that gives you the ratio of C over A. Okay, this value is from the table. You refer to the table. Okay. Ideal number for C over A is 1 over 6. 1 over 6. So how to find this number? Okay, you go back to this table. This one. Okay. You go back to this table. This one. Okay, this one. This is HCP. How you get the value of C, either directly from the table or from this ratio. If it's cadmium, then you either straight away from the table and you calculate. Okay. Again, memorize 3 member from here. 3 member from this table. The rest, this one you read. This one you read is for your reference. We won't go deep into this one. We only look at these 2. Under cubic, you have 4 types. Simple cubic, 3 types. Simple cubic, BCC, FCC. Hexagonal is one of it. So total you have 4 types of cubic system. Then this is a simulation on how it's being packed on HCP. So if you are seeing that one layer, one layer, one layer, one layer like that, it's called ABAB stacking sequence. It's like stacking X. One layer, one layer. Okay. Okay, this one I go very fast. You go home and have a look. So this example 2 is to calculate the zinc crystal structure using following data, and it gives you the zinc having HCP structure. You are having A and C. Then you find the volume of the last cell. So from this table, you go to zinc. Pure zinc is this one, 0.265 and 0.747. Of course, if this kind of question come out, but if you see this one in the appendix, this value A and C won't be stated in the question anymore. If you see this table, HCP table in the appendix, you won't see A and C value inside the question because we expect you to refer to this table. Okay. Okay. So by using the formula of this one, so you draw the HCP, the frame out of the unit cell out. So how you draw? You draw six corner, then 6 corner. Then you break into half. You draw the half, and then you draw the half. Basically, you're connecting all the corners. You draw 6 corners, and then you draw the line connecting each other. Then you get the center. Repeat the same for the top. Then you label A, B, C, D, E, F, and the C and the A on the diagram. Okay. So you're calculating the value for the volume. All right. Volume. So if you look at this one, you're having 6 unit and you have an A there. So again, trigonometry. This is a right angle, not a right angle, 2 right angled triangular. is A and H. So basically, it's a same side triangular. So same side triangular you can make into half with the right angle. One triangular is 180 degree. You divide by 3 because it's the same side. So each side is 60 degree, 60 degree, right? You draw half. This one 60, this one 90, this one is 30, right? Okay, then you have the h of height here. Okay, so you continue. Area of the base of the unit cell is ABCD. A, B, C, D. You're able to find the area of this one multiplied by 2. You're able to find, right? How do you find area of this one? Half base multiplied by h, right? How to find the area of triangular? Half height and base, right? Multiply by 2 because this is parallelogram. It's a triangular, sorry. So once you find the area 1, multiply by 2. Okay, so it means it's a 2 triangular. So you put in the formula, 2 half h and h cancel. You get h multiplied by a. So what is h? Because we don't want this parameter h, we convert h into a common sense, which is a. So a is this one. You have a h. So how to find h? You use trigonometry, which is a sine 60. Okay, go home, go and think how to get a sine 60 using this diagram. Okay, so cancel 2, you get square. So a square sine 60 is your area. Okay, you have the a, right? Substitute a there. Press calculator, you get the answer. But again, I want to highlight this one in nanometer, n power -9. Be careful on the unit. In this module, if you don't put it unit, you forget to put unit, automatic discount 50%. If the answer is 2 marks, you only get 1 mark for the answer. Let's say the answer is something, right? Then you forget. Okay, volume. Volume is to, once you get the base, right? The base you let's see. Okay, C multiply by the area, right? Okay, you'll get 0.03 nanometer cube. This is for HCP volume of the black color one. The black color unit cell. Because A here is calculate the black color area. You multiply by the C, you get this black color cube. Not cube lah, but black color volume. Okay. Okay. Then you continue. For the total large volume, you take the single black color volume, multiply by 3. Because you have 3 set here. 1, 2, and 3. You take this number, multiply by 3. Okay, get the answer. Sorry, is yeah. Sorry, because original I forget to remove that one. Okay, so this is how you solve for HCP. The start actually not difficult, it's only your understanding. Okay, you draw HCP, then you break into 6 cube, label A, label C, then you use trigonometry derivation to find the relationship of A and H, substitute back, find the area of these two triangular, multiply by the C, and then that is a primitive cell. You have 3 primitive cell. So the question, if you ask you last cell, means multiply 3 primitive cell. Okay, Okay, with this, we stop here. Huh? Correct. This one, this equation. Okay, stop here.